Hi, this is Karthikeyan. So here I would like to explain the second module in D block elements. So in the second module, what we are going to discuss means, see here, we are going to discuss about the physical properties. Physical properties. In these physical properties, D block elements, how they are generally. They are ductile in nature, they are malleable, they are tensile in nature, they are lustrous, and as well as they are conductible in nature. But we know this is in small class onwards, we are discussing, we know the metallic characters, ductile, malleable, tensile, lustrous, and conductible. Next, coming to the point, atomic and ionic radius, if you see, means how the trend will carries in this D block elements or trans elements once, if you see, means see here. So atomic radius generally see from this graph we can understand scandium, titanium, vanadium, chromium, manganese. Slowly it will get decreases. Slowly it will get decreases. See here in this graph, if you see, means it is gradually get decreases, and then it will maintains constant atomic radius in these three cases, iron, cobalt, nickel cases. And then here in copper to zinc, copper and zinc cases, if it means it will get increases. So this is the trend will takes place in each and every series, like in 3D series, 4D series, and in 5D series also the same thing will happens. So here I expand in the next graph, see. So in 3D series, if you see, means here scandium, titanium, vanadium, chromium, manganese. Up to here, the atomic radius get decreases, and then iron, cobalt, nickel. In this case, it will maintain a constant. That means a similar atomic radius, and then from copper to zinc, the atomic radius again it get increases. What is the reason behind it? In each and every case, why it happens in 3D and 4D as well as in 5D series? Why this trend taking place like this means here, see, from scandium to manganese, the atomic radius get decreased because of this reason, due to effective nuclear charge. Effective nuclear charge predominates the screening effect here. Because of that reason, here the atomic radius gradually get decreases. From iron, cobalt, nickel. So from iron, this iron, cobalt, nickel, if you compare, these are, we can say, as a successive elements. In successive elements, there is no difference, that much of difference in their atomic radius. Why means here effective nuclear charge and screening effective will take place in equal ratios, equal strengths, so that these are exhibiting similar atomic radius here. Here see, copper to zinc, if I compare, means, so here screening effect is predominating effective nuclear charge. That's why the atomic radius get increasing. Now, what is effective nuclear charge and what is screening effect? That you have to know here. Effective nuclear charge is nothing but it is the resultant nucleus attraction forces. Resultant nucleus attraction force. Here expensive. For example, this is one nucleus we are having. Nucleus. Around that, we are having some shells or orbits. I think these are the orbits. And here we are having last shell. This is the last shell. I think this is the last shell where the electrons are present. So in inner shells also many electrons will be present like this. So these are inner electrons. Okay, now what will do, these electrons, what will do means, this will repulse these inner electrons. The outermost electron will repulses the inner electron. This is the repulsion will takes place. In the similar way, see, this will screens the nucleus attraction force. Up to this, it won't move. Okay, so this, what will do? This inner electron will do two things. One is it will repulse the outermost electron. Another one, it will screen the nucleus attraction force. After screening the nucleus attraction force, what resultant force will be moves up to the valence electron? That force is called as, that resultant charge is called as effective nuclear charge. Effective nuclear charge. So effective nuclear charge means the resultant nucleus attraction forces which will goes up to the valence electron is effective nuclear charge. Okay, screening effect means already I told. So the electrons which are present in the inner shells that will screen some of the nucleus attraction forces, that is called as screening effect. That is screening effect. Now where effective nuclear charge will be high, and when compared to screening effect, there the atomic radius gradually get decreases due to attraction of nucleus on the outermost electrons. Okay, Next here, see, effective nuclear charge and screening effect. Both are taking place with equal strength. With how much strength the nucleus is attracting towards itself. The nucleus attracting towards itself. In a similar way, that inner electrons also opposing. Okay, inner electrons also opposing that nuclear attraction forces. These are opposing the nucleus attraction forces. Okay, so that here the sizes are similar in case of iron, cobalt, nickel in transition triads. Next, copper, zinc. If you see, means here screening effect is huge. Whenever screening effect is huge means nucleus attraction cannot move up to here. Okay, see here, nucleus attraction force is huge. Sorry, screening effect is huge here. Whenever screening effort is huge, so nucleus attraction force cannot move up to the valence electron. This is the valence electron. So here the nucleus attraction force is not moving. Up to here it is not moving. It will be screened up to here only. Okay, here only it will get screens out. So that gradually the size will get increases. Okay, that is the reason why the irregular trends or irregular atomic radiations will be in this 3D, 4D, and 5D series will be. So that is a brief introduction about atomic radius as well as ionic radius. Next, coming to the point. Let's see here. Here what I try to explain means, so before cases I explained, no? So effective nuclear charge, how it is, if it is equals to screening effect means what happens, those and all things I explained. Next, as a result of this decrease in the atomic size here, lanthanoid contraction, okay, actinide contraction, these things will take place. What is meant by lanthanoid contraction? From lanthanum to lutetium, due to large size and less shielding effect of 4f orbital, the outermost shell electrons attracts towards the nucleus strongly. As a result, from lanthanum onwards, the decrease in the size will take place. This is called as lanthanoid contraction. So see here, what I'm explaining, due to large size, actually f orbital, if you see, means it's a diffuser shape. These are having diffuser shape, large shapes they are having. So, okay, because of the large shape of or diffuser shape of f and d orbitals, especially we are discussing about f, so that I'm saying about f only. F orbital, because of having a diffuser shape, it cannot hold the nucleus attraction force. This nucleus attraction force it cannot hold. So that what happens? So we can say f orbitals are having poor shielding effect. So that what happens here? The nucleus strongly attract the outermost electron. For example, 6s electrons. Some electrons are present in 6s outermost shell. So they will be attracted towards the nucleus strongly. As a result, what happens? The decrease in the size, the contraction in the size will take place. That is called as lanthanoid contraction. Once again, see, due to large size of these 4f orbitals, the outermost shell electrons, okay, these will strongly attract by the nucleus. As a result, the decrease in the size will take place. That is called as lanthanoid contraction. Okay. Next, here only we'll discuss what is actinide contraction also. That also I'll explain. Okay. First of all, before going to that actinide contraction, because of this lanthanoid contraction, what are the consequences of this lanthanoid contraction we'll discuss here. Generally, if you see, atomic radius will get increases from top to bottom. If this is the atom, next size this will be, next it will be like this, next it will be like this. The size of atom must be increased like this. But due to lanthanoid contraction, okay, size won't get increases this much. Okay, even though it will increases somewhat, but it is not that much easily identified. Okay, so that is not differentiable. It won't be that much of differentiable increase in the size. Okay, there is a slight change only. That means those two atoms, the first atom and the next atom in the group means they will have nearly similar sizes. For example, see here, zirconium is having 206 picometers of atomic radius. Hafnium is having 208 picometers. Similar radius only, see. What is the reason behind it? Means because of this lanthanoid contraction only. Because of this lanthanoid contraction. Actually, the size of atom should be increased, but due to lanthanide contraction, here the size of atom is looks like similar. Okay, so that is the reason. That is one of the consequence. So atomic radius will be similar. Next thing is what? Actually, whenever the size of atom get increased means its metallic character should increase and it should act as a good base. But due to lanthanide contraction, what happens? Size of atom get decreasing. That means similar sizes are decrease in the size will takes place. Due to decrease in the size, what happens? Non-metallic character increases, basic nature will get decreases. Non-metallic nature increases, acidic nature increases, basic nature get decreases. As an example, lanthanum hydroxide and lutetium hydroxide, if you compare means. So lanthanum hydroxide to lutetium, if you go, what happens? The basic strength gradually get decreases. Basic strength gradually get decreases because of decrease in the size. Otherwise, due to lanthanide contraction, it get decreases. That is one of the consequences we have to discuss here. Next, actinide contraction. Due to this actinide contraction, what happens? See, here also same. So there 4f orbital, no, here 5f orbital. Due to poor shielding effect of these 5f orbitals, okay, 5f orbitals, the 7s electrons, the electrons which are present in this 7s level, they will feel high nucleus attraction forces from the protons. Okay, so these nucleus will strongly attract towards itself. As a result, the nucleus size, the total atomic size will get reduces. There see, lanthanide, then there in lanthanide 4f, because of 4f 6s, here because of 5f orbital in actinides. Okay, in actinides, okay, what happens here? The 7s electrons strongly attract towards the nucleus like this. Okay, as a result, the contraction or decrease in the size will take place. Okay, right. That is the thing I wrote here. Due to poor shielding effect, of 4f, 5f orbital, 7s electrons which are present in the outermost shell strongly attracted towards to nucleus. As a result, from actinium onwards, decrease in the size will take place. Okay, this is called as actinoid contraction. That is the thing I explained here. Next, what are the consequences of this actinoid contraction? So, as a consequence of actinoid contraction, actinide's size almost the same like lanthanides. So, covalent character increases. Before also explained there, covalent character get increases as the size of atom decreases according to Poisson's rule. Covalent character get increases. See here, and as a result, basic strength get decreases. Acidic strength increases, basic strength decreases. As a result, if you see, if you compare actinium hydroxide and californium hydroxide, which is having highest basic nature, which is having least basic nature. Here's the covalent character. If you compare this covalent character here, means actinium hydroxide is having less covalent character. This is having highest covalent character. Why? The size of actinium is here. This much means californium, this much. Size get decreasing because of actinide contraction. So basic nature will be, basic nature here it will be high. Okay, high basic, this is highly basic. Highly basic. Which one is highly basic? Which is having high large size, that is highly basic. Which is having least size, that is least basic. That means californium hydroxide is least basic, we can say. So as a consequence of this actinoid contraction, these things will take place. So these things we had to discuss here. Next, coming to the point. Next is ionization energy. So how ionization energy will take place? What is the trend in these groups as well as in periods we have to see. First of all, what is meant by ionization energy? So the amount of energy required in order to remove an electron from a neutral gaseous atom, that energy is called as ionization energy or ionization potential. So once again, see ionization energy definition: the amount of energy required to remove an electron from a neutral gaseous atom, that is called as ionization energy. Now in groups, what happens? See, when you are coming from scandium, first of all, I'm taking this scandium third B group. So in third B group, scandium, yttrium, lanthanum, actinium, the size will be like this. Titanium, zirconium, hafnium. So lanthanum, what happens? Atomic radius get decreases, no? So that means lanthanide contraction will take place, no? As a result, here see, zirconium and hafnium are exhibiting similar atomic radius or atomic sizes. As a result, when the atomic radius will be similar, then what happens? The ionization potential also will be nearly equal to each other. See, 660 and here 600. Okay, nearly same. They're exhibiting nearly same atomic radius. Nearly same ionization potential values they are exhibiting. Okay, that is the trend that will take place. Next, if you see here, one of the example I explained, see here, ionization potential, how it will varies. So copper, silver, aurum, zinc, cadmium, mercury. If you compare this, so this is very important bit we are having. When you compare copper and aurum, silver is having less ionization potential. Why? They will ask. And when you compare with zinc and mercury, cadmium is having less ionization potential. Why? What is the reason? See here, with some values also I'm explaining here. Copper, its ionization potential is 745 kilojoule per mole, and silver 731 kilojoule per mole, and aurum means 890. Okay, actually when the size of atom get increases means the Rm should have least ionization potential value. Why? Whenever the size get increased means, then what happens? Nucleus attraction force will be get decrease on its valence electron. As a result, we can easily remove this electron by using less amount of energy. But here, amazingly, this exhibiting highest ionization potential values. Why it is? The same way, in zinc 906 kilojoule per mole, cadmium 868 kilojoule per mole, mercury 1000 kilojoule per mole of energy they are exhibiting. Okay, this much of energy they are exhibiting. Why this irregularity is taking place means, here the reason I'm explaining, see here. So first of all, why copper is exhibiting highest ionization potential means because of small size. That we know very well, it is easy. So copper and zinc, why copper is having highest ionization potential than silver means, when compared to silver, copper size is small. Because of that reason, from there onwards, if you want to remove electron means much amount of energy we have to use, okay, in order to overcome the nucleus attraction forces here. Okay, right. Next, why here in case of Rm, it is having highest ionization potential values when compared to silver means. See here, is stable. One reason is stable D10 configuration. Stable D10, completely filled configuration present means there onwards if you want to remove electron, that is highly difficult. Next, effective nuclear charge also increasing here. Effective nuclear charge means the resultant nucleus attraction force, that also increasing. Due to increase in the nucleus attraction forces, resultant attraction force if it get increased means, so here, there also it is difficult to remove. That's why, because of these two reasons. What are the two reasons? Stable electronic configuration and effective nuclear charge. Because of these two reasons, here it is difficult to remove the electron, so that it requires much amount of energy. The same way here also, say a small size, because of small size when compared to cadmium, it requires much amount of energy, 906 kilojoules. Here 1000 kilos, why had used means here stable D10 configuration as well as effective nuclear charge is high. Because of these two reasons, here also mercury is exhibiting highest ionization potential when compared to cadmium. This is one of the important bit we are having here. Next comparison I'm going to expand. See, ionization potential 2 I'm going to expand here. Ionization potential 2. That means second ionization potential. Second ionization potential means what? After losing first electron, the second electron, if you're going to remove by using certain amount of energy, that is called as ionization potential 2. The amount of energy required to remove the second electron from a uni-positive ion is called as ionization potential 2. So first of all, I'm comparing here chromium and manganese. Chromium is having highest ionization potential when compared to manganese. Chromium is having highest ionization potential than manganese. Why it is like this? Chromium, whose atomic number is 24 and its electronic configuration is 3d5 4s1. After losing this electron, 4s1 electron, this is IP1. The amount of energy required to remove the first electron, that is IP1. Now second electron, if you want to remove, means see, this is half-filled configuration. We know half-filled configuration always stable, right now? Half-filled configuration always is stable. That's why here onwards, if you want to remove electron, means high amount of energy we had to use. High amount of energy. So that ionization potential 2 of chromium is greater than manganese. Next, manganese, 3d5 4 is 2, atomic number is 25. First electron, by using certain amount of energy, if you remove this first electron, no problem, easily it loses. Second electron also, valence electron also, that it easily loses. Second electron also, if you are going to remove means, okay, then what happens? Here also, after losing first electron, second electron also, it will easily loses. So that here no problem in this case. Okay, that's why chromium second ionization potential is greater than manganese. In a similar manner, ionization potential 2 of copper is greater than zinc. Why it is? Copper, if you see 3d10 4s1, its electronic configuration. After losing this one electron from 4s, the second electron, if you want to remove, means it is highly difficult. Why? Again, here it is completely filled configuration. Completely filled configuration we can see. Completely filled configuration means what are that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. From this completely filled D10 configuration onwards, if you want to remove electron, means it is highly difficult. Much amount of energy we have to use. That's why ionization potential 2 of this copper is greater than zinc. Next, zinc case, if you come means first electron it is losing. Okay, one electron is losing. Second electron also it is easy to remove. So there is no problem in this case of zinc. Okay, so that's why copper ionization potential, second ionization potential is greater than zinc, and chromium second ionization potential is greater than manganese. Next, I'm going to compare here ionization potential of D block element and S block elements. So D block elements and S block elements, D block and S block, if you compare means, so D block is see D block is greater than S block generally. Okay, why D block elements are having highest ionization potential values? High ionization potential these are exhibiting. Why these are exhibiting high ionization potential means, when you compare, see here, these are D block, S block elements. S block elements, for example, first A group, this is second A group. Okay, so when you are coming from first year, second year, and then D block means what happens? Size of atom gradually get decreasing. See, size gradually get decreasing like this. When size of atom gradually get decreases like this, what happens? Definitely nucleus attraction force will be acts on the electron. So it is very difficult to remove the electron from here. So much amount of energy you have to use here. Okay, that's why ionization potential of D block elements are greater than S block always. Okay. Next, here I'm expanding. The next thing is ionization potential in periods, otherwise in series. In periods, otherwise in series, how the trend is taking place. See here. For example, if you are coming from 3D series onwards, this is the 3D series: titanium, vanadium, chromium, and then manganese, iron, and then cobalt, nickel, copper, zinc. That means, see here, generally ionization energy is increasing from scandium to manganese. Manganese having highest ionization energy. That means it is showing highest energy, ionization energy here. See here. And then after reaching to the iron, these are exhibiting ionization potential values nearly similar ionization potential values they are exhibiting. Okay, and then copper to zinc, if you see, means ionization potential values get increasing here. Okay, so what is the trend takes place here means scandium to manganese ionization potential will gradually get increasing due to decrease in the sizes. So ionization potential values, why it get increasing? Due to decrease in the size, it is increasing. Next, iron, cobalt, nickel, here because of similar sizes, similar atomic radius, here these are exhibiting similar ionization energy values. Okay, and then copper to zinc, if you see, means here zinc, in case of zinc, again the ionization potential values are get increasing. Why ionization potential values get increasing here means, again because of 3d10 configuration and effective nuclear charge. Due to effective nuclear charge and 3d10 configuration, zinc is exhibiting highest ionization potential values. Okay, here another trend what you have to see, in the successive elements, in between the successive elements, the difference in the ionization potential values will be nearly same. See, successive elements means, for example, iron, cobalt, nickel. If you will take iron, cobalt, in between these two, the difference is less. In between these two, cobalt and nickel, the difference is again less. So, in the ionization energy difference between two successive elements, in general is less. That is the point I have to discuss here. Next, see, ionization energy in case of chromium and copper, if you see, means first ionization, see, chromium case if you will take means chromium and copper, its ionization potential, one is less ionization pressure 2 is always high. Why it is already, I think you are getting some idea. See, its electronic configuration is 3d5 and 4s1. Losing this electron is easy. By using less amount of energy only, we can remove this electron from here. Okay, so but from the 3d5 configuration onwards, if you want to remove the second electron means, which is a very stable electronic configuration, it is highly difficult, so that we cannot remove the electron that much easily. See, 1, 2, 3, 4, 5. From here onwards, if you want to remove electron, is much amount of energy we had to use. That's why ionization energy is less in case of chromium, ionization energy 2 is high. Next, copper also same. In case of copper also, the first electron from 4s onwards, if you want to remove electron means it is easy. From 3d10 onwards, if you want to remove the electron means high amount of energy you have to use, so that it is difficult. Ionization energy 2 of copper is high. Next, zinc. Ionization energy 1 is generally it is having somewhat high energy. Why means completely filled configuration. Next, it is ionization energy 2 is easy only. Okay, ionization energy 3 again it is difficult. Why? After losing C4s2 here, if you want to remove electrons, certain amount of energy you have to use. So highest ionization energy we have to use here. Why highest ionization energy we have to use here? So here it is exhibiting 3d10 completely filled configuration as well as effective nuclear charge getting increasing. So that high ionization energy, first ionization energy, these are exhibiting. So after losing the first electron, second ionization energy is easy. Okay, second electron easily we can remove. But third electron, if you want to remove, means 3d10 onwards we have to remove. So that again the ionization energy 3 will get increases. That is the trend you have to remember by seeing this graph. Okay, so that is the same trend will take place in 3D series, okay, and then 4D as well as in 5D series. Okay, right. Next, after completion of this one, next topic. So next thing here we have discussed that density. How density will get varies. So density is nothing but mass by volume. Within this unit volume, the number of particles in mass will be considered as a density right now. So here, if you see, when the size of atoms gradually get decreases from scandium to copper here, see here. So gradually when the size of atom get decreases, here what happens, density will get increases. So highest density who will exhibits means copper will exhibit highest density 8.96 gram per ml. This is okay, that much of highest density among the total 3D series, copper will exhibit highest density values. Again, the density in case of zinc, it will get increased. Why? So within the here volume get increases, the atomic size of this zinc will get increases. Within the volume, the number of particles what will have, that will be get decreases. As a result, here density will get decreases in case of zinc. Okay, that is the trend you have to observe here. So due to poor shielding effect, already we discussed lanthanide contraction as well as actinide contraction due to 5f and 4f orbital poor shielding effects. Okay, close packing will take place. Very close packing will take place. As a result, densities will get increases. So that here, as a consequence, copper will exhibit highest density, that is 8.96 gram per ml. Next thing, what I have discussed means here, enthalpy of atomization. So what is enthalpy of atomization? Enthalpy of atomization is nothing but from the constituent particles, where we are going to convert the constituent particles into its atomic form. See, the amount of energy required to convert constituent elements into their atomic forms, that is called as heat of atomization. Okay, heat of atomization. For example, H2 molecule are having this H2 molecule, if you are going to convert into hydrogen atoms. So in order to convert this into hydrogen atoms, what energy you are going to use here? That energy is called as enthalpy of atomization. So the constant particle or constant molecule, if you are going to convert into atomic form means atomic forms means that is called as enthalpy of atomization. This enthalpy of atomization will depends on the number of unpaired electron present in the particular species. Number of unpaired electrons. Okay, right. 1 second, wait. So enthalpy of atomization means I told. So the constant particles, if you are going to convert into atomic form, that is called as enthalpy of atomization. So certain amount of energy we are going to use for that, that is called as enthalpy of atomization. That will depends on number of unpaired electrons, I told. Number of unpaired electrons. When this number of unpaired electron increases, interatomic attraction forces get increased. Whenever the number of unpaired electrons increases here, interatomic interactions will get increases. So in between the atoms, interatomic interactions will get increased. When number of unpaired electron increases, attraction forces, number of bonds get increased. When the number of bonds get increased, interatomic attraction get increases. As a result, enthalpy of automation will be increased. That means high amount of energy we had used. Understood here? When the number of unpaired electrons get increases, one species having one unpaired electron means only one bond it can form. If another species having two unpaired electrons means two bonds it can form. Three unpaired electrons are present means three bonds it can form. Okay, five unpaired electrons are present means they can form five bonds with the other species. So whenever they will form number of bonds, whenever the number of unpaired electron increases, number of bonds get increases. 1, 2, 3, 4, 5 like this. Number of bond increases. When the number of bond increases, we can say interatomic attraction forces are getting increasing. When the number of interatomic attraction forces are increasing, it is difficult to break these bonds. Right now, see these many bonds it has to break. So it is difficult to break bonds. So much amount of energy we have to use. So enthalpy of automation get increases as a result. So here enthalpy of automation as well as ionization energy and hydration enthalpy, these and all will results the standard reduction potential values. This is one of the factor. It is one of the important key factor for determining standard reduction potential values as well as chemical reactivities. Chemical reactivity and as well as standard reduction potential values we can identify with the help of enthalpy of automation and ionization potential as well as hydration enthalpy values. Okay, this is one of the key factor, important factor in order to identify standard reduction potential as well as chemical reactivity. Now see, so in our NCERT textbook also we are having this graph. So based on this graph also they will find some questions. It's an experimental evidence. This graph is nothing but an experimental evidence which explains that 3D series elements are having highest enthalpy of automation than 4D and 5D. So this graph, see here, this graph indicating, see, first of all, the red line, this is nothing but 3D series elements. 3D series elements are having highest enthalpy of atomization, that it means. Next is 4D series elements are having next category. Next level who are having means 4D series. These are having next level enthalpy of automation. Next level who are having means 5D series. 5D series elements are having next level of enthalpy of automation. So enthalpy of automation, if you compare means 3D series are having high and then 4D and then 5D series elements. It's an experimental evidence we are having. So we have to know this. Next, if you see, zinc, if you see means zinc is having less, that means 126 kilojoule per mole only, very less enthalpy of automation. Why it is? Why it is having less enthalpy of automation? So here we can say zinc atomic number is 30 and its electronic configuration argon 3d10 4s2. 3d10 means completely filled configuration. Completely filled configuration present means, see here, completely, if the d orbital filled means there is no bond formation, there is no, see, completely filled, due to completely filled d configuration, this zinc do not form many bonds with others. So that as a result, what happens? Interatomic forces or attraction force will get decreases. Atomic forces decreases. Whenever these interatomic forces get decreases means, as a result, what happens? Less amount of enthalpy, less amount of energy only we can use in order to convert this zinc into its atomic form. By using less amount of energy, we can easily convert this into atomic form. That's why its enthalpy of automation is very less. Why it is? Because of stable D10 configuration. Okay, so next thing what I have to discuss means, next we have to discuss about melting points. Melting and boiling points we have to discuss here. So melting point, if you see here, melting and boiling point, if you see here, transition elements, they will exhibit high melting and boiling point. What is the reason? Due to presence of many number of unpaired d electrons. Number of unpaired, due to presence of number of unpaired electrons. So interatomic forces increases. As a result, by using a high amount of energy only, we have to break that bond, so that it requires a high melting points, high boiling point they will exhibit. In case of zinc, cadmium, mercury, if you see, because of having no unpaired electrons, no interatomic forces will be, if there is no inter-attraction forces between them, it is easy to break. That's why they will exhibit low melting and boiling points. Next, these are very hard and low volatile in nature. Transition elements are very hard and low volatile. What is the reason? Here, why these are very hard and low volatile means because of participation of Ns as well as N-1 d electrons. In these transition elements, not only ultimate shell electrons, here penultimate shell electrons also will be involved in the bonding. So that because of that reason, here very strong attraction forces will be takes place in between the atoms, so that they are very hard and they are low volatile in nature. Okay, this is about melting point and boiling points. In any series, if you see, if D5 configuration, if you can able to observe, means there it will exhibit high melting point. In this case, some of the exceptions also is there, but in general, D5 configuration, if you are able to see, means that will exhibit highest melting point. One or two exception cases we are having, that also we'll discuss. For example, observe this graph carefully. 3D, for example, chromium 3D series I'm taking, where it is having 3D5 4s1. So 3D5 4s1, if it is having, means see, in 3D series, this is 3D series graph, chromium is exhibiting highest melting point. This is a melting point graph we are having. Chromium is exhibiting highest melting point in 3D series. Okay, so it is satisfying. Where D5 configuration will be, there its melting point will be high. What I said, that is correct. Next, 4D series, if you see, means 4D series, molybdenum. See, molybdenum is exhibiting highest melting point. See, here also D5 configuration we can able to see D5 configuration. Because having D5 configuration, this molybdenum also is exhibiting highest melting point in 4D series. Next, here one exception case we have, not one, two exception cases we are having. Even though tungsten is not having any D5 configuration, okay, it is exhibiting highest melting point. This one exception case we have to remember in your mind. Next, manganese, even though they are having D5 configuration, half-filled configuration, D5 configuration, half-filled configuration, stable half-filled configurations, manganese as well as technetium, these two are having half-filled configuration even though, but these are exhibiting, say, manganese and as well as technetium, these are exhibiting low melting points. It's an experimental evidence. In each and every case, we are having some exception cases. Here, from this graph, what I have to understand means, in general, where D5 configuration will be, means their melting point will be high. So two exception cases we are having, that is, even though manganese in case of technetium, they are exhibiting 3D5 and as well as 4D5 stable configuration, but its melting point is less only. And another exception case is, even though tungsten is not having any D5 configuration, that means it is having only 5D4 6s2 configuration, no D5 configuration, but it is exhibiting highest to melting points. Okay, so these exception cases we have to remember properly. This is very, very important. Next, after completion of this one, the next topic is, so next part here, in the second, regarding the second module, we have to go with this objective part. In this objective part, first bit, see which element exhibits highest density in 3D series. Which element exhibits highest density in 3D series? We know in 3D series, if you see, scandium to copper, the density get increases, and zinc it will get again decreases. Scandium, if you see, means this is 2.9, this is 8.96. Next here, these are 7.1, this is 7.1. So like this, the density values will be. Okay, so highest density who are exhibiting means copper is exhibiting. So in 3D series, generally scandium to copper density get increases. Then in zinc, if it means zinc, because of its large volume, the number of particles will be less, so that its density will be get decreases. Whose density? Zinc density will get decreases. So here if you see, means scandium 2.9 and chromium is 7.1, zinc is 7.1, and copper is 8.96 gram per ml. What is the density values? The maximum and minimum melting points of first and second transition series respectively are. So the maximum and as well as minimum melting points of first and second transition series. First and second transition series means 3D series and 4D series they're asking. So 3D series if you see means easily you can identify that is chromium, highest melting point. Maximum melting point is in 3D series maximum melting point chromium. Next, first in second means in 4D series the least minimum melting point they're asking. They have to give here cadmium, but they didn't give here. Cadmium is having least melting point. Its melting point is 321 degrees Celsius only. Its melting point is 1900 degrees Celsius. So these are having highest melting and least melting points in first and second series. That means in 3D and 4D series. Next, coming to the point, the following does not show variable valency. Which of the following does not show variable valency? We know very well. Zinc does not show variable valency because of having its completely filled configuration, 3D10 4s2 configuration, they won't show variable valencies. Zinc. Element which can show +2, +3, +4, +6, +7 oxygen states means that is manganese. Manganese will exhibit all these states +2, +3, +4, +6 and +7 oxygen states. Next, coming to the point, which of the following pairs of element have same radii? Already we know zirconium and hafnium because of lanthanoid contraction. Because of lanthanoid contraction, here zirconium and hafnium are exhibiting similar atomic radii. Next, coming to the point here, which of the following ion is colored in its aqueous solution? Which of the following ions are colored in its aqueous solution? Titanium we will take here, titanium +3. So titanium actually is scandium, titanium 22. So argon, its electronic configuration 3d2 4s2. Okay, after losing these 2 electrons from here, after losing 1 electron from here, the resultant electronic configuration will be like this. That means at least one unpaired electron is present in titanium +3. That's why it is colored. But if you take this one, scandium as an example, scandium +3, that also I will show. Scandium +3, its atomic number is 21. Argon 3d1 4s2. That means 2 electron from here and 1 electron from here. That means completely all electron left out from here means then nothing will be. There is nothing means no colored ions. If any at least one unpaired electron present, then only they will exhibit colors. Next, maximum IP values. IP value in 3D series. Maximum IP, scandium, titanium, scandium to zinc efficiency. Zinc is having highest ionization potential value. Why it is? Because of 3D10, stable electronic configuration. Stable electronic configuration, and because of having effective nuclear charge, highest effective nuclear charge. Because of these 2 reasons, it exhibits highest ionization potential values. Next, coming to the point, the second ionization potential of copper is very high. The second ionization potential of copper is very high due to the configuration of what? So copper, if you see, it is 29th atomic number and its electronic configuration is 3d10, argon 3d10, 4s1. So from here onwards, if you want to remove this electron means that is ionization potential 1. The amount of energy required to remove this electron is ionization potential 1. So the second ionization potential after losing this 1 electron, it becomes U plus 1, where it is its electron configuration argon 3d10, 4s0. From here onwards, if you want to remove electron means huge amount of ionization energy you had to use. Ionization 2 you had to use here. Okay, so that is 3d10 configuration. Next, coming to the point here, variable valency of transition elements is on account of why variable valencies the transition elements exhibits. Why means because of incompletely filled d orbitals. Because of this reason, they will exhibit variable valencies. Next, coming to the point, transition elements show generally positive oxygen states. Why? Why transition elements will show positive oxygen states means because of low ionization energy values. Because of having low ionization energy values, they will exhibit positive oxygen states. Next, the maximum oxygen state of ruthenium. Ruthenium, what oxygen state will exhibit means ruthenium +8. That is the maximum oxygen state that will be exhibited by this ruthenium. Next, coming to the point, which of the following is a correct statement? Aqueous solution of copper plus and Zn+2 are colorless. We'll see. Cu plus will take. So 29, argon, and this is 3d10 4s1 plus 1 means it loses this electron. After that 3d10 Zn plus 2 will take here, whose atomic number is 30, argon, and this is 3d10, sorry, this is 3d10 4s2. After losing these two electron, here it is 3d10 only. Okay, both are having stable and completely filled d10 configuration, so that it won't show any colors in its aqueous solution. This is correct. Next, Mn plus 2, Mn plus 3, Mn plus 6, Mn plus 2, Mn plus 3, Mn plus 6. What colors they will exhibit? They are asking here. What colors they will exhibit means they will exhibit pink color, they will exhibit blue color, they will exhibit green color. This is very important thing. So what colors these Mn plus 2, Mn plus 3, Mn plus 6 will exhibit means PUBG. In a simple way, you can easily remember this. Plus 2, plus 3, plus 6. PUBG. Pink, blue, green. In that way, just remember, it is easy to remember. Next. Pink, blue, green. That means first option. 4 successive members of the first row transition elements are listed below with their atomic numbers. Which one of them is expected to have highest third ionization enthalpy? They are asking. So scandium, titanium, vanadium, then it is chromium, manganese, and then iron. These are the first 4 successive elements they given. Which one of them is expected to have highest third ionization energy? So manganese having highest third ionization energy. So how it is exhibiting highest third ionization energy? See, manganese 25 its atomic number, and its electronic configuration we see is argon 3d5 4s2, 3d5 4s2. Now see here, I'm going to expand 3d5. So 3d5 1 2 3 4. Sorry, 3, okay, 1 2 3 4 5, and this is 4s2. So first electron we are going to remove, that is first ionization energy. Next, second electron if you are going to remove means that is second ionization energy IP2. So third electron if you are going to remove here means see half-filled stable configuration came. From this stable half-filled configuration, if you want to remove this electron means much amount of energy we had used. So ionization energy 3 is high. In which case means in this case of manganese. Next, coming to the point, which of the following factors may be regarded as the main cause for lanthanoid contraction? What is the main cause for lanthanoid contraction? Is because of poor shielding effect of 4f electrons on another in the subshell. Because of 4f electron, poor shielding effect of 4f electrons, the nucleus strongly attracts the valence electron towards itself. As a result, the size of atom from this much to this much will get reduces. This is called as lanthanoid contraction. So thank you for watching my video. So I hope all of you understood till now what I explained. In the second module, we are going to discuss about the remaining some of the important compounds like potassium permanganate and potassium dichromate and its properties, preparation, as well as its chemical reactions. And then the actinide compounds we are going to discuss. Thank you very much. Have a nice day.